Welcome back. So, this is the member seminar. Those of you who have been here before, you know that BIMSA used to have this core seminar series, member seminar, in which faculty introduce themselves. That's the idea. The idea is not to discuss technical things. The idea is to tell people what is it you do as a faculty member. And actually, sometimes our distinguished visitors also have been invited to give talks. So we had a hiccup in the middle, really, because there was a decision to have colloquium seminars. BIMSA also has a colloquium series. And so we just thought, if it is the same thing, then why should we have two seminars? So for a while we canceled it, but then Professor Yao insisted that actually we should have both. We will have colloquium and we will have member seminars, in particular because member seminars mainly focusing on faculty talking about the research. Colloquium mainly focuses on our visitors or our invitees to talk about the research. Okay, so the idea is to give simplified talks, and this is okay. And we spend a lot of time to make sure the talks are accessible. I need to tell you who are the co-organizers: me and Hussein, and Yuval Perez, and Bart has recently joined. Thanks for joining. It's pleasure to have Peter Koroteev, who will talk about geometric aspects of integrable systems. Go ahead.
Thank you very much. Hello, everyone. It is my pleasure and honor to talk to you about my research. So, as most of you know, I'm a member of algebraic geometry group. So, I'll give you some unique perspective on geometric approach to integrable systems. So, let's begin. So, I hope this is okay with everybody. Let's look at harmonic oscillator, right? So, it's becoming like a cliche, like, as harmonic oscillator, like as easy as harmonic oscillator. So let's give another look at this. So this is the energy function of a harmonic oscillator. So imagine you have a particle in the parabolic potential, and then if you let it go, the gravity will pull it down. As it goes down, its kinetic energy increases, its potential energy decreases, and it passes the equilibrium, goes back, and it goes up and down. Right? So here, x is the coordinate of the particle, p is the momentum, and h is the energy function. Now, using methods that most of people in the room I hope know. So there's a way to derive equations of motion given this energy function, which are called Hamilton equations. So you would take the partial derivative of this function with respect to momentum gives the velocity, and then the negative partial derivative with respect to coordinate gives the derivative of the momentum, the acceleration. And therefore, if you combine these two equations, you get this familiar equation of the second degree, whose solutions are linear combinations of sine and cosine. Now, geometrically, we'll look at this slightly differently. So let's plot p and x on the plane, and then this equation will give us a circle, right? So, and this is the energy level equation for an oscillator would give an energy E, which is like the value of h. Now, this is what is called symplectic manifold, meaning that if you have this two-form dp wedge dx, it's non-degenerate everywhere. And although this example is pretty simplistic, similar systems has symplectic manifolds, and on those you can define the non-degenerate symplectic form. And then the circle here, the energy level of the system, is what is called this Lagrangian submanifold. So it's a half-dimensional, middle-dimensional subset on which the symplectic form vanishes. So in this case, again, it's a one-dimensional system, but this is also true in general. Okay, so what is integrability? Now, you can also write those. So say you have some function of coordinates and momentum of your system, and then you can show that, well, its evolution, its time derivative would behave as the following combination. So these are called Poisson brackets and equations given over here. So it's a certain anti-symmetric combination of partial derivatives with respect to coordinates and momentum of the system. Now, and integrability is the following phenomenon. So if your system has n degrees of freedom, it's like n particles or something like that, then integrability implies that exactly n of them are conserved independently. So the technical definition is a bit more complicated, but roughly speaking, think of having not just one H, but there's H1, there's H2, so usually it's a momentum, energy, but also there are what is called higher charges. So those what scale, which are cubic in momentum or quartic in momentum, and so on. Now, if this sounds strange, trust your instincts, right? So it's something very bizarre. So like, if you kind of, so the reason why you probably didn't hear about integrable systems, like in elementary school or in middle school, is because they should not exist. It's like, in fact, in quantum field theory, there's a theorem that essentially tells us that they should not exist because of certain general, requirements. However, in the existence of integrable systems, we can think of them as certain asterisks. Like there's a certain special case, which only works in some very special cases. It's like, like pandas. Like, so pandas are very rare. They should not exist, but we try to preserve them. And, people in Chengdu Zoo, they try to do it as hard as they can. You release them in the wild, they still cannot survive, right? So this is how we should think about them. Now, remember that circle. So it turns out that this is what happens in general. So this is called Liouville-Arnold theorem. It says that those Lagrangian submanifolds, right? So energy levels of the system, they are diffeomorphic to tori. So like circle is one-dimensional torus, then have a two-dimensional torus, and so on. Now it's a stronger statement. It's not just homotopy equivalent, like topologically equivalent. It's actually diffeor. So there's like a map which is differentiable in both directions. So it's a very strong statement. And then often, if you kind of zero down on the neighborhood of those Lagrangians, then around those, the evolution of the integrable system is linear. So it's a very simple equation. So before you had coordinates and momenta, but now you have what is called action and angle. So actions are conserved, and angles, they just rotate. Okay. And then, so in principle, no, never mind. So if you find those variables, then you're done. You have solved the system. But it's actually hard to do, and it's art as well as science. Now, some examples. So all problems that you studied in middle school, whatever, they're all integrable simply because you can solve them. So example would be point particle, oscillator, planets moving around the sun. In fact, this system here with planets has even more conserved charges than you need. It was called super integrable. So it has more than n. It's like more than half, but not all of them are independent. Second example are those many-body particle systems. So you imagine you have a one-dimensional system like a circle, and those particles they live in a circle, then interact with each other with some long-range potential that depends on positions of those coordinates. Yet another example are spin chains. So you have spins up and down. For example, you can have spin up, spin down, and then spins interact with each other with some kind of spin chain, lattice Hamiltonian. Okay, so these are and then see some of them are continuous, some of them are discrete. Another continuous example are those 1 + 1 dimensional systems. So the most famous one is KdV. So I'm sure most of you have seen this equation. It's so famous that people write it on T-shirts, right, for this triple derivative of the in the right-hand side, and then it describes scattering of solitons, like propagation of fluid in shallow water. So see, like they scatter through each other without any dispersion, right? And so you can kind of think of them as point particles. They're kind of, if you look on the center of soliton, there's a point particles, and then if you kind of ignore the intrinsic structure of those, you'll get back to this kind of system. In fact, that's what people do. Like, say, let's have some number of particles. If those number of particles becomes infinite, you have something continuous like this, or you can go backwards if you only look at the centers of those solitons. Well, you must admit it looks pretty satisfying to see them scatter. Okay, so now this is the last board by Richard Feynman. So it's in Caltech archive. It was taken on the day of his death. And then he wrote here, over here, to learn. It says Bethe-Ansatz problems. So Bethe-Ansatz problems are certain techniques that were invented in early 20th century to solve lattice systems like spin chains. And then he wanted to learn them in connection to other stuff, other things that are written on the blackboard. So it says some like Kondo problems, so physicists in the room can relate to that, two-dimensional Hall effect, and so on. Actually, I kind of like the way he crossed out Kondo, kind of, so Feynman learned it, like, good for you, Richard Feynman. So now he knows what Kondo is. Also, if you look at the top left, it says, what I cannot create, I do not understand. Or know how to solve every problem that has been solved. As you kind of towards the end of people's career, people become more philosophical and sort of think through the results that have been obtained all over the place. But most importantly for us today, he said the following. So it was not on the board, but it was written in one of his most recent papers, latest papers. So I got really fascinated by these 1+1 dimensional models that are solved by the beta ansatz, how they mysteriously jump out at you and work, and you don't know why. I'm trying to understand this better. So my research is an attempt, well, it follows kind of this direction. So we're now trying to understand those systems better using geometry. Okay. So as Artan likes to say, we are geometers first, right? And then algebraic geometers. So there we go. So we have integrability and geometry going hand in hand. So like there's like it's almost a joke. So there's mathematical physics. So in fact, there are two jokes here. One, like, what is modern mathematical physics? The answer is everything but. So everything but PDEs and this. And second joke is like if you swap the order of the words, it's a term which was coined by my Rutgers colleague Greg Moore, who says that, well, you can think of physics motivated or physics informed, how we say, research that allows us to prove mathematical statements, mathematical theorems. And what I'm working on is kind of in this direction. So here are a couple of bullet points, which I'll hopefully have time to be able to illustrate. So first, the geometry provides a universal framework to study those models. Like all of those models that I showed in a couple of slides ago, they naturally live in the world of geometry. So it's a natural habitat. Coming back to biology analogy, right? And then, and also kind of as a feedback, integrability helps to calculate some geometrical problems. Like for example, curve counting. Like in enumerative algebraic geometry, people study spaces of maps of various kinds. And often, if you can find integrability there, you can just guess the answer. Essentially, you solve some PDE or some ODE, and you get the answer right away. And then as the propagation, kind of as the feedback in the other direction, geometry helps to prove dualities between integrable models. Okay. So here's some papers recently. So kind of funny, like, so, some of you know that I was a physicist in previous career, and this is my first like math paper. Like you can see the date. 2017 was in archive and 2021 was published. So I got hit hard by the math community the first thing. So I'm sure there are people in the room who can beat this record. More than 5 years, right? So anyhow, so yeah. And then sort of most recently, so I have another seminar lining up a couple of weeks ago in number theory group. So it connects to many things. But yes, like if you actually want to read details about those papers, you can send to the slides. You can just, it's clickable, so you can download all the papers. Also, you can see 2023 was a pretty good year. Yeah, so I wish every year was like 2023. Now, here's well, some of you have seen this map. This is the world map of physical mathematics from my point of view. I know, so I'm, as you can see, I'm fascinated by the language, by Chinese culture. So, well, the name for China is Zhongguo, right? Meaning this is a central country, that everything is in the middle. So the object that I'm about to introduce in a couple of minutes is called opers, right? And turns out that it plays certain pivotal key role in understanding connections with other things. Like, and then if you're good in geography, so if this is China, kind of if you go east, you'll go to, west. From here, you go to Europe. If you go east across Pacific, you go to the States. So America is a beautiful country, apparently. Meiguo, right? So the way Chinese do this, they pick words that are phonetically close and give them some nice meaning. Like, so Meiguo, beautiful country. De Guo, kind of moral country. Fa Guo, like it's well, right means both law, legislation, and right means not left, right? So, and then you can see that France here is, where's France? Yeah, Grothendieck, enumerative geometry. Now, what is this? Chinese guys don't answer. Which country is this?
That should be South America.
One. So Sergio, where's Sergio? Italy. Italy. So this is phonetic, right? So I put number theory because, well, no, it's China, so it's a conformal. Anyhow, so sort of Italy for number theory, for honor of Fibonacci, and Sergio, of course. Right. Yeah. Anyhow, so in a time remaining, we'll have time to fly across North Pacific to America and to England for many body systems and to, well, we'll see. Anyhow. Yeah. Okay, so let's begin. Let's do actual geometry here. So let's consider Riemann sphere, CP1, okay, and U is the local coordinate on CP1. And let's have what is called a vector bundle of rank 2. Now, what does that mean? It means that on every point, there's a fiber, which is a copy of two-dimensional complex plane, C2, right? And then in that plane, I can pick a vector, so it's called a section, right? Now, because it depends on the choice of this vector depends on the position on this P1, it's called the base. The section will depend on that local coordinate as well. Okay. And then, of course, from linear algebra, we know that any vector spans, if you take a span of it, we have a one-dimensional vector space. So this L will be a sub-bundle, right? Because we have a bundle, so there's a kind of on every point there's a two-dimensional plane, right? And then inside that plane you have a one-dimensional line. Okay, so that's what bundle is. Now we need some more structure, so bundle isn't just enough. Then we introduce the multiplication. So pick a complex number q, which is non-zero, and for convenience it's not equal to 1 or any of roots of unity. And then imagine take a complex number and multiply it by that q. So in conformal maps, we know what happens. We have a complex coordinate. We can stretch the complex plane and we can rotate it by the face, right? So you can kind of imagine this q multiplication is a certain rotation of that CP1, right? So if you have a point here, after the q multiplication, it moves over there, right? And then you can ask, how can we connect the fibers after we shifted the coordinate by this q? And this is done with what is called the connection. Q connection, what the name suggests. So it's a linear map. It's a matrix from C2 to C2. So it's a 2x2 matrix, which also depends on the position of this point Q. So because it connects values of the section at u and qu, we can think of A being giving you the differential, a difference equation in this case, right? So, and you can just solve it without any geometric connection, but of course, geometry is what we're after here. Okay, and finally, one more ingredient is called the gauge transformation. So imagine I change the coordinate to a different coordinate, right? So here, G of u is a certain 2x2 matrix, which acts like a gauge transformation. And in this case, I can ask myself and convince myself really quickly that the connection matrix will be transformed like so under this gauge transformation. So now what is oper? Well, it kind of stands for operator, and then there's some dark story for that. For this, I recommend reading Edward Frankl's book. But dark story aside, so oper is part of the operator, and then the condition for the oper is this. If you have a vector, this section over here, so what happens if you have a vector and you acted on it with a matrix? It rotates the vector, right, and maybe stretches this, but if the matrix is from SL2, the length stays the same. So just the vector rotates around. So we're going to require that after action with my matrix, with the connection, the vector becomes linearly independent with the original vector. Okay, so in other words, after you take a section which spans the subbundle, and then if you act on it with a matrix, you go into the complement. Right, so this is C2, so C2 mod C is also C, right? It's one-dimensional thing, and then essentially we're requiring that there's no singularity, so like after action by the matrix, we don't just stretch it, we actually kind of rotate it around. Okay, so that's what the oper condition. Now let's break it down a little bit. No, difference equation is just a thing in itself. It's like I'm saying, if you have a connection, you can write a difference equation. Oper condition is the condition on the connection. So for any connection, good. So yeah, so this is okay. So here I haven't given the oper condition yet. So for any connection, you can write the difference equation. But some connections are special. In other words, those which satisfy this condition are oper connections. So oper connection is a subset of all connections. Again, there's difference equation for every connection, oper or not, right? So yeah. No. It's like, okay. So this is, you can say, let me impose, okay. So let me impose this condition. You can study space of solutions of this equation. It's like a separate question, okay? I'm just saying this is a certain requirement that I'm imposing to, as Artan said, carve a locus in the set of all connections, okay? No, I think, okay, guys, like, so if I give you the ODE, right? So like f prime prime equals f, right?
You wrote two equations, right? SQ equals A times U, and SQ is not proportional.
Oh, I see what you're saying. You want to plug it in? Yeah. So if you want to put a different letter there, but yes, like so. This is just a so for every connection you can write a difference equation. Does it make sense? Yes. Yeah. Pure connection. That's all. That's all this equation says. Other questions?
What is oper?
So oper is a bundle, right? With a sub bundle, right? Generated by S, satisfying this condition. So it's a bundle with connection, right? Together with this condition. For every S. It's a non-degeneracy condition.
Write it down in terms of its visualization locally, in terms of coordinates, and that's an equation.
Yeah, that's right. So if you want a formal definition is this. So it's the if you take a bundle with a sub bundle, then the following map is an isomorphism. So you take bundle factor over the sub bundle, take the pull back under the Q, and it should be isomorphic to the sub bundle itself, right? Which means the following interialization. So we say the if you have a vector, so you compare the vector after the Q shift and after the action of A, right? And it simply tells you that these two vectors are linearly independent. That's what the condition is. Okay. Let's move on. So now, so we want to introduce some singularities here. So in fact, the right-hand side cannot vanish. So before it was non-zero, but now I'm going to introduce a polynomial of degree n. Okay. Whose roots I'm going to call a sub c. So there's like a1, a2. So those are isolated singularities on CP1. Okay. And then, in other words, if I hit the singularity, then these two vectors are actually going to become parallel to each other, right? So, that's one condition. And then second condition, I want to be able to transform my connection to a diagonal matrix, right? So this matrix takes values in SL2, like in the group SL2. So locally, I want to assume that I can gauge diagonalize it to this matrix over here. So with this in mind, we can write, so now let's do it again. Take a section, I'm going to parameterize it with Q plus and Q minus. Q shifted section, Q plus of QU and Q minus of QU, right? And then the action of the connection in the diagonalized form. So you're going to have this thing. So now my oper condition tells you that this vector and this vector are linearly independent. Okay? So here we go. We can write it as a Wronskian. So we can think of a determinant of a matrix whose columns are formed by the first vector and second vector is non-zero. Or if you have singularities, it should be equal to the polynomial, which I introduced earlier. Now, of course, I hope you recognize the difference version of what is called the Wronskian here. Right? If you have an ODE, you can have a determinant of a matrix formed by function, derivative of the function, second derivative of the function, and so on. So this is the Q version of that Wronskian. Okay, and now the SL2. So if you compute the determinant 2 by 2, you'll get this equation over here, which is called the QQ system. So see, it's a Q difference functional equation on those functions, Q plus and Q minus, of second order, right? In this case, because you have Q shift in one direction and a Q shift in the other direction, right? So QQ system appears in many parts of well, mathematical physics that includes a category of representations of affine Lie algebras, algebraic combinatorics, like well, here also in integrable systems, like it's a thing on its own, so that's why it lives in a beautiful country. Okay, so this is the QQ system. That was one connection. Now let's see how it connects to the spin chain. Okay, let's take this equation. So say Q plus is a polynomial of degree k, right? Whose roots are S sub L, so there are k of them, and then let's assume that they do not collide with the singularities. Okay, and lambda is here again. So these are two polynomials. Okay, so now I can evaluate the left-hand side at roots of Q plus and the right-hand side of the roots of Q plus, and I can do it twice. I can do it before the Q shift and after the Q shift. And I'll get this equation. So on the left-hand side, I'll have, well, it'll be, well, if I evaluate this on the roots of Q plus, the first term vanishes, so I get this. And if I evaluate the roots of Q shifted Q plus, then this is equal to 0. So I divide one by the other. And if I substitute the definition of those polynomials, I get what is called the beta ansatz equations for XXZ spin chain. So there's a certain polynomial equations in those variables S. So here, the degree of the polynomial lambda that parameterizes singularities tells me how many sides on the spin chain I have. Degree k tells us how many of those spins are up. And this equation tells me the energy level is sort of, if I solve this equation and solve it for those variables Si, I will find the energy for my spin chain Hamiltonian within that sector. So when I have k spins up and n minus k spins down. So people in the well, in physics and integrable systems, they've been studying these equations for almost 100 years. Kind of this is the geometric way to see how they appear in our constructions. Essentially, the beta ansatz is a condition that is equivalent to the oper condition for this choice of data.
Is it Q related to standard definition of Q difference calculus?
Q difference what?
Calculus. Like Q extension of differential.
Sure. I mean, like I said, so you can. So in fact, there is a version of opers without the Q. So there's a version where instead of Q connection, I have regular connection. Then I'll have a actual gauge transformations, not the Q gauge transformations. I'll have an OD here and not the difference equation. Yes. Yeah. It's a certain reduction from my construction. Yeah, absolutely. Yeah. So there's a whole universe of those opers. I'm just giving the most intuitive example that connects with the results in integrable systems. Okay. So we have a little bit more time. So now, second story is the algebraic geometry, right? So we're going to France now. So there's yet another way to see this system over here. So there's another way to see, sorry, a spin chain with k spins up and n minus k spins down. Namely, so there's a topological space which is called Grassmannian of k dimensional hyperplanes inside n dimensional complex space, right? So so think of it, so it's a big space, right? So whose points are those k hyperplanes, right? And then you can do it for every k from 0 to n. So imagine you have the following setup. So you have, well, this is kind of the linear algebra realization of that space. You have a bundle of rank k of some sort, right? So it's parameterized by k variables, s1 to sk. And then you have a trivial bundle, which is like a constant, which is, isomorphic to just n-dimensional complex space, which is parameterized by variables a1 through an. And then you can think of this quiver variety as the space as the following. So first you take the map. First, like you have matrix A, which goes from V to W, and matrix B that goes back to W. Right? So it's a composition of two matrices. It's a certain map, and then pre-image of 0 of that map, modular the simultaneous conjugation by matrices of GLK, right? This defines a certain algebraic variety, right? So it's called, in this case, it's called cotangent bundle to the Grassmannian, but the details are not important. What's important is that it depends on these two integers, k and n, right? So again, so think of k spins up, n minus k spins down. And then the way the beta ansatz appears from here is when we study action of the maximal torus of this group here. So you can take coordinates on Cn and then scale them with independent parameters a1 through an, and then fixed points under the section are parameterized by combinations of of number of ways to draw k balls out of n boxes, right? So, and the same combinatorics appears in spin chain. So there are n choose k ways to have k spins up out of n in your spin chain. And then so what we call k theory is a certain algebra which depends on those variables s1 through sk, and these are the relations in classical k theory. And in quantum k theory, well, it's a certain deformation where we study space of maps from CP1, from a curve. So it's a different Riemann sphere but it's a source of this map into this space, right? And then we integrate of the moduli space of this of those maps. So there's additional parameter Gothic Q here, which acts on the CP1 on the source curve, and so the result of this calculation is a certain infinite. So this is a polynomial map of some degree. So say if f is a polynomial map of degree d, then in each degree you will have a contribution which is a certain rational function of all those variables. And then in order to get this equation, so you need to take the series and then take an asymptotic limit when this parameter q goes to 1. And then you'll see that in certain asymptotic approximation, this equation will pop up as the certain saddle point approximation of those equations. Okay. 1 minute to when you start. Yeah. Okay. And then finally, one more application. So remember, I also had this many body systems. So let's take the determinant again. So it's a Wronskian of these functions, and then let's take q plus to be a linear polynomial and q minus to be a linear polynomial. Now you can see that you have a determinant of the 2 by 2 matrix. So it's characteristic. So and you can write it so you can write the determinant as the following thing. It's like a u minus t. So it's linear in this because polynomials are linear. The determinant will also be linear. And then if you do your algebra, you'll see that the characteristic polynomials of degree 2. So its first coefficient is what's called h1, second coefficient is called h2, and if in the right hand side you also have degree 2 polynomial, you have a match. So h1 equals a1 a plus plus a minus will be the energy level equation for this integrable system. It's called Rosinar's model. So here, so p's will be the momenta. Remember in the first slide we have momenta. A's will be the coordinates, and q. Actually no, yeah. So zeta is the coordinate. So zeta, I remind you, is the twist of the oper. So it's the eigenvalue of the connection. Zeta, yeah. So q is the coupling constant, and p's are the momentum. So yeah. So that kind of completes the. Let's get back to the map again. So we had, so we talked about how opers do QQ systems, many body systems, and great ansatz. Okay, that's it. Thank you.
Okay, questions?
Thank you. So I know that opers have been used, for instance, by Frankel and Fagin to give a description of the center of the completed universal enveloping algebra of a Kac-Moody algebra, the
That's right.
empirical level. So do
It's
these?
kind of it's on the side, yes. Like they are those, so they cover QQ systems in that
And
regard.
the Q opers do they have some similar interpretation?
It's just Q difference generalization. Yes. So any result you know about opers or differential equations, you can Q deform. Yeah.
But I was asking about this connection to the Kac-Moody algebras. Is there something?
Well, it's not on my map, but yeah, it's part of. So the way it's related is that they get QQ systems as some relations in in the growth and decreasing of this category O of representations of UQ of B plus. And it's the same QQ system.
I see.
Yeah.
Okay. Thanks.
That's right.
Questions?
You said that it is related to the evaluative geometry. So what are you counting using the opers?
So there is no. So yeah, it was just a similarity for like we get the same result, right? So like there was no direct way to embed oper here. So just sort of a small like similarity of the approach. So so these are relations in quantum K theory of Grassmannian, right? And they also coincide with the Q-oper conditions. So just you get to the same equation, same result from two different directions.
But she's asking, what is it you're counting?
No, she's asking, does oper count anything? And the answer is no, it doesn't count anything. Yeah. So the similarity is this, right? So is the equation itself.
If you use torus equivalent geometry, you could be counting things. So those could be partition functions of genus zero curves inside Grassmannian
but she was asking whether the opers like literally like is there any way opers directly enter this picture?
Yeah.
Right.
But the partition functions are similar to Gromov-Witten invariant.
Yeah, sure. So this is the quantum class, right? This is like this is the like people who do Gromov-Witten. That's exactly what they have. So you have like tau, you put a descendant into one of those fixed points, right? So if your quasi map is relative at that point, you can put it there, and you can do the equivariant localization.
So one question is, if you instead of counting vector bundles inside that other bundle, trivial bundle, you count torsion-free objects. So instead of counting things in Grassmannian, you count things in the Hilberty scheme. You can do it using opers. Can you do it?
Well, I need to look at the results in the equation. I hope so. Yeah, this is something that I want to look into. Yeah. It sounds promising. At least like given like the data that you need, maybe I need to introduce some additional structure to my opers construction. So, yeah.
And then this map, this curve, can you do it for genus 1?
Not sure because I need like this kind of see here. It's important that all fixed points are isolated. I'm not sure how to do it, how to make it. So like in a, like see the torus like yeah. So so here I'm not sure how to make it this part. So the fixed points should be isolated on the moduli space, right? Not just on the target, but for the full moduli space. If you pull it back, so I don't think genus 1 would work. At least not in obvious way.
No, I mean the fixed. Oh, those are fixed points of your ambient variety.
No, yeah, that's right. So,
So
you
if
should
you
think
take
of
CN
this torus
of
and this one is an extended torus. Yeah.
Okay.
This.
Sorry, didn't Sokolov introduce opers to describe hierarchies? Do you know anything about Q-deformant version of hierarchies that can be related to your opers? Q version of this, of course.
Say it again, please.
So Drinfeld Sokolov introduced opers to describe hierarchies that integrable and then have rich structures. Do you have kind of Q version of this?
Absolutely, yeah. So I can have the Q version, like I can write you the DS version of the Q connection. Yeah, definitely.
And then you have what? I mean, some simple example of Q hierarchies. What does it mean?
Some Q deformation of those. Yeah, I can show you later. Yeah.
Okay.
More questions from the audience also at Xinhua? Okay, let's thank the speaker again.